Good morning, everyone. So we're going to work on this lecture review packet. I can maybe take some questions during the packet and also in general during class. Let me say, if you ever have questions in class, feel free to raise your hand, interject at any point today and in future lectures as well. The question on Friday's survey of how prepared do you think you are for midterm one, or how worried are you about midterm one? Not a lot of people were confident. So hopefully the weekend has helped. I mean, that was the weekend before. Maybe a lot of studying went on for the midterm. But hopefully over the weekend through today and tomorrow, we're becoming more confident heading into our first midterm. Okay, so we're going to start here with this question. So the diagram's depicting nitrogen atoms with the black spheres and hydrogens with the white spheres. And so this molecule here, well, this diagram here is depicting molecules. So this might be something like NH3, and we see 4 of those molecules depicted in the diagram. So I definitely see a molecule because that just means we have 2 or more atoms bonded together. Even if I had 2 nitrogens bonded together, that would be a molecule. Even if I had 2 hydrogens bonded together, these would both be molecules. So the word molecule would still apply to these guys here as well. The only thing molecule wouldn't apply to would be a single atom, like helium or something. If I saw a helium atom, that's just an atom, not a molecule. And then maybe if I saw the alternating structure where I have something like this, where I see alternating spheres. I'm not doing a good job drawing it, but if we had some alternating plus minus, that might be better as a compound, not a molecule. So if I'm trying to depict sodium chloride solid, for example, this is maybe a bad diagram of that. But if I'm trying to picture something like this, that's probably not a molecule, but it would be a compound. So, you know, things that aren't molecules, molecular compounds, this might be better described as being an ionic compound. But just a little nuance there for a few variations of this question. But so what else we can call NH3? Of course, it's a compound. So if we have 2 or more elements, then it also would be a compound. So NH3 is also a compound. So molecule would apply, compound would apply. We could call that a molecular compound. The terms uniform throughout would also apply because the sample is randomly distributed. We don't see like a phase. We don't see a left side versus a right side or a top versus bottom. We see 3 or 4 randomly distributed molecules. So the diagram showing something that's random throughout, uniform in structure. And then the variable composition is really asking the question, do I see 2 or more different compounds or molecules or substances present? So I see 4 identical molecules. So that means we have a non-variable composition. So a variable composition would be, I see 2 different substances. I see NH2, I see N2 molecules. I see H2 molecules. So in a different context, we see a box that looks like this, and then we see something that looks like this, and then something that looks like this. So this would have a variable composition. So I'd have maybe H2 molecules, N2 molecules, and the composition would vary depending on which molecule we're looking at. So just trying to make sure we understand what the terms are meant to imply for variable composition is that the molecules are different. Since the molecules are the same, then we have a non-variable composition. So all of these statements here, or all those terms would apply to this diagram. So then I'd kind of just review some terminology out of chapter 1. And so some of the terminology is for chemical versus physical change / reaction. And so a physical change or reaction would be something like a temperature change, maybe a pressure change, and also a phase change. So think about changes that aren't changing the underlying connection between the atoms and the molecules in the sample. Once we start changing the molecular bonding, the types of covalent bonds or the bonds between our atoms, think about a reaction like H2 plus O2 going to form 2 water molecules. So this is an example of a chemical reaction because we're changing the type of bonds. We're changing bonds between 2 hydrogens and 2 oxygens to that between hydrogen and oxygen together. So chemical reactions involve the making and breaking of bonds. So things that lead to a color change, things that lead to an explosion, things that lead to maybe an irreversible change would be something you're thinking would be signs of a chemical reaction. Something where you just take a solid, raise its temperature, becomes a liquid, lower its temperature again, it becomes a solid again. That's just a phase change. That's just a simple physical change. So that's one of the topics in chapter 1. A pure substance versus a mixture. Now, one of the things with a pure substance is it's like a hypothetical. Like rarely and almost never can you truly have anything 100.00000% pure. So when we say something's a pure substance, we're meaning 99% plus pure. So you can have pure water, or you could have sodium chloride or sugar or something dissolved in water, where we'd have a mixture. So you can have 2 or more substances present in the substance that you're looking at, or you can just have one component. And you can have some very minor impurities, so don't make the mistake of overthinking a problem. Like if we say you have a sample of water, is that a pure substance? Yeah, it's pure. Like it's not going to be 100.0 out to infinity pure, but it's close enough to pure that we call that a pure substance. Just to make sure we get the difference between a pure substance versus a mixture. A mixture is something where we maybe intentionally add a component to like a liquid and dissolve it in it, perhaps. We see terms in chapter 1 for element versus compound. We just hit on those in the previous slide. So a given atom is said to be of a particular element based on the number of protons in its nucleus. And so compounds are comprised of 2 or more elements. And then any given atom is said to be of any particular element based on how many protons are in its nucleus. So a molecule is where we have 2 plus atoms connected together. So again, the big, thing that we like to test on is like something like N2, because it's an example of a molecule, but not a compound. So it's a molecule, not a compound. I have at least 2 elements for the substance to be a compound. And it's something a little confusing. When we say element, sometimes we're trying to imply, like, there's a question I never liked when they put this on the test. I try to not have it on the test because I think it's overly confusing. A question would be on the thought of, if you took sodium and oxygen and react them together, like what phase would the reactants be in? And it just kind of sometimes catches you off guard if we aren't very clear and try to get you to think of, well, what is the actual form of sodium in nature at room temperature? Our metals are all solid with the exception of mercury. So if you know the element's metallic, then you know it's going to be solid. So if we're thinking of, how does sodium appear at room temperature? Sodium's a solid because we know it's a metal, has to be a solid, it's not mercury. And then when you have a non-metallic element, it's not necessarily always going to be a gas, but a lot of them are gas, and a few of them are diatomic molecules. So I think it's good to know, like if you're going to run a reaction like sodium and oxygen at room temperature, it's probably going to look something like O2 gas and not oxygen atom, because O2 is the most stable form of oxygen. So presented in chapter 2, and I think this is mentioned briefly, is that H2, N2, O2, F2, Cl2, Br2, and I2 are the diatomic molecules of the non-metallic elements. So these are the elements that exist as diatomic molecules. And I think these are pretty common because H2, really common, N2, O2, really common. And these are just the halogens. And then they're all gases except for bromine and iodine, bromine being the liquid, iodine being the solid. And I don't necessarily think you need to memorize or know for a fact that bromine and iodine are liquid versus solid, but I think it's just kind of interesting to see most of these are gases, and as you get bigger towards bromine, liquid, even bigger towards iodine, solid. And so if you're going to think of, if you ever have a question of how elements are reacting, they would have to be in their most common state that they would exist in. So sodium's not a gas, oxygen's not a single oxygen atom, it'd have to be something like O2. Now, if you had to predict a product here, this kind of comes back to a chapter 3 topic. Remember, our metals and nonmetals were making ionic compounds. So we'd be making something like our oxide. So we'd make that oxide of oxygen as its common ion, sodium plus for sodium. And then we'd have to do some balancing here to get 2 oxygens, and then 4 over to sodium. So we can kind of turn a question of just kind of what is, how does sodium exist at room temperature, sodium solid, how does O2, or how does oxygen exist at room temperature, O2. The name of oxygen is just oxygen, like O2 is oxygen. We don't have to call it molecular oxygen or dioxygen. It's just oxygen. We breathe in oxygen, O2, not O atom. So a couple little minor nuances with kind of naming as it relates to atoms, elements, compounds, etc. So these are elements here. O2 is a molecule, molecular molecule, how O2 exists, and then we form the compound sodium oxide here in this particular example. So let's look at this question here. So this, the questions on atomic weights, sometimes there's a few things we want to make sure we keep in mind. So let's look at the question and try to see what we should kind of put into a question like this. So in nature, we're told here magnesium consists of 3 isotopes, meaning it naturally exists as 3 different isotopes. And then a sample of magnesium was measured using a mass spectrometer. That's how we determine the individual atomic weights, if you recall, for isotopes. We can do this for molecules too, but for an element, you can feed in the element, get the abundance of the isotopes it exists as and their abundance data. You can get the atomic weights of the precise atomic weights of those isotopes as well. And so then we do this for magnesium, and then where the atoms were separated base. So the mass spectrometer, what it's doing is it's putting a charge on the atom and then separating the atom on basis of the mass to charge ratio. So the different isotopic masses separate and allow their detection. So that's how the mass spectrometer is working. And so here we're presumably detecting, if this is the right answer, detecting mass to charge 24. This would be the mass number 25, and then this one being the mass number 26. The one thing I think I want us to pull out from our analogies of a lot of different examples of atomic weights is that a given isotope has a mass near a whole number of AMU, because the isotope would have a whole number of protons and neutrons. And protons and neutrons have masses very close to 1 AMU. Now, you can't just know the mass of a proton and a neutron and look at a given isotope and add up those particles, because we have something called nuclear stability that lowers the mass of that nucleus. But the mass of the isotope will be very close to a whole number of AMU. So when I'm looking at an isotope of magnesium-24, its mass should be pretty close to 24 AMU. Not dead on, it's not going to be 24.0000, but it'll be probably like 23.96 something or whatever. So when I see options like this, like is this what a mass spectrum of magnesium might look like? Probably not, because no isotope should have a mass possible between 24 and 25 AMU. So if we look at magnesium in the periodic table, the average atomic weight's 24.3. So that's another thing we need to pull into this question, is knowing we can kind of check the periodic table, and that we can see the average is 24.3 for magnesium. So I need to know I can check the periodic table, and then somehow when I average the 3 abundances, when I take the average, when I take the sum of the fraction of each of those isotopes times the atomic weight of that isotope and sum that up over all averages, that this has to sum up to 24.3 AMU. Okay, and so one way I can average to 24.3 would have been choice 3 if that were possible. Because what choice 3 is looking like is we have a big peak around 24.3 and then 2 smaller peaks equidistant on either side, which would average out to 24.3. The only problem is no isotope can have that particular atomic weight. So the reason why choice 3 would be wrong is just because it would be very unlikely for an isotope to have that particular atomic weight. Choice 4 would be wrong because it's showing an equal proportion of isotopes at 24, 25, and 26. This would be wrong because what would the average atomic weight of magnesium been if this were the actual abundances of its isotopes? Wouldn't have been close to 25. So if the atomic weight, if we looked it up and it were 25.0, then we'd probably think choice 4 was correct. But it's not 25.0, so So choice 4 is right. So think about what the average atomic weight would be if we had the abundances shown in box 4. We'd get an average of 25.0. That's not right. Box 2 also would average out to about 25 because we see roughly equal peaks either side of 25, most abundant peak at 25. That would also average out to about 25. And that's not the right average. And so then having the most abundant isotope perhaps be 24, and having lower abundances at 25 and 26, those are going to push our average a little bit off at 24, but not by much, because those abundances are really low. So imagine you had a problem where you had, say, 90% at mass 24, 5% at mass 25, 5% at mass 26. You could even do that math if we're just kind of trying to eyeball this and say 0.90% is 24, so 0.9 times 24, and go 0.05 times 25, plus another 0.055% at mass 26. I keyed it in wrong. Let me try to fix it real quick. That gets me 24.15. So that's getting me off of 24, close to 24.3. If I wanted to calculate it exactly, I need more precise atomic weights and more precise abundances. Yeah.
So my question for you was that if the atomic weight or the atomic mass average would be like 24.8, would that then round to 25, or would it still be 24?
Well, if we look on the periodic table, it said 24.8 is what you're saying.
Yeah.
Like what I would say, well, I don't know if we'd be able to come up with what choice here is best, but what I would think is it would probably look something like 2 or 4. It would look like something like 2 or 4 where 25 would probably be more abundant and maybe a little bit shifted towards 24. So it might just look like, imagine this is a little bit higher than this one, so it's a little bit offsetting just less than 25. So like these questions are always kind of silly because they're just trying to kind of present you with some data that then allows you to think of, can we roll any of these choices out? And I think we can roll out 2 and 4, and just we can't roll out 1. And 1 is the one that makes the most sense because we have the highest peak at 24, the average is right around 24, and the peak's a little bit higher, or just making it not exactly 24.0. Is that? Okay. Okay, so these atomic weight questions, there's also numerical versions of the question that I was going to say, I think there's a question in here as numerical, so let's go to the numerical version of the example. So there's the thought example where we kind of can give you some data, like a mass spec. There's other versions of the question where you could say, a given element has 2 isotopes. And like a way without even necessarily doing hard numbers would be, like sometimes I've seen problems where it says boron has 2 isotopes. I'm going to make up the math here. But I'm going to say that boron, which we can look up, its average is 9.01. Is that what that says? 10.01? Oh, I was looking at beryllium. Okay. I was like, my eyesight must be terrible. I was looking at beryllium. But yeah, boron, you're right. 10.01? Oh, 10.81. Yeah, so like 10.81. And let's say boron is a mixture of boron 10 and boron 11. This may or may not be true, so don't. And so if you know boron could be boron 10 or boron 11, and you know the average is 10.8, like can you predict the abundances of boron 10 versus 11 without even touching a calculator? Hopefully we can, because this should have a mass of about 10 AMU. This should have a mass of about 11 AMU. And if we're averaging at about 10.8, we're going to be about 80% boron 11. Just that's the only way the math could work, because we'd have to be that much more abundant on the 11, and these would be the only 2 possibilities. So no other isotopes are possible. If this were the case, we're going to be about 80% boron 11. The other 20% would be boron 10. And so then we can do this with math too. So we can throw some numbers into a problem where we can play around with the numbers. Actually, 8's a really easy question in a way, because 8's telling us that, that iodine exists as a single isotope. And so given that we now know that iodine exists as just one isotope, and that isotope's iodine-127 is its only natural occurring isotope, what's the atomic weight of that isotope? Just periodic table. So we can just go to the periodic table, and it's 1 126.9045. I think some other periodic tables might go a little bit more precise, but this would be the average atomic weight of iodine 127. So you'd have to know that that's the only isotope iodine exists as, and then we can know we can go to the periodic table and get that atomic weight. Now it's not exactly 127, so that's why it's not D. And then I think A is the answer you might get if you just add up all the subatomic particle counts. We can't just add up the subatomic particle counts to get that number. Now let's look back at this boron example, because I don't think there's another math example in here for atomic weights. Like, what if we wanted to calculate that number precisely? What if knowing 80% roughly wasn't good enough? What might we do? Well, what we can do is just use that equation that the average atomic weight would be equal to the fraction of the lower isotope, the fraction of the boron 11, times the atomic weight of boron 11, or excuse me, I said boron 10, the lighter one's boron 10. So let's do the fraction of boron 10 times the atomic weight of boron 10, and then plus the fraction that's 11 boron times the atomic weight of boron 11. And let's say we're using these numbers as given, 10.0, 11.0 AMU. One key is that we have to know this average is given on the periodic table, which was at 10.81. But then the one thing that the problems would want us to do, and there's a problem recitation last week that went through this, is that the fraction of the two possibilities have to add up to 1. That if it's either one or the other, then the two fractions have to add up to unity. And that's just basically saying if it's 50% one, it's 50% the other. If it's 30% the one, it's 70% the other. But in fraction, it would just be 0.5 the one, 0.5 the other, 0.3 one, or 0.7 the other. And so what we can do, like let's say we want to solve for the fraction of the 10 boron isotope. What we might then do is solve for the fraction of the 11 boron isotope, how it's 1 minus the fraction of the 10 boron. And then we can sub this in here and then go back through the math. So we can sub this in here, have this 1 minus the fraction of the 10 boron, and have one variable where we can then solve an algebraic expression. So might be a little bit of a mess. Let me rewrite this real quick. So we'd have the fraction of the 10 boron times the atomic weight of the 10 boron. Let me write that as 10 AMU. And then the sum, so plus 1 minus the fraction of 10 boron times 11 AMU. And that's all equal to that average atomic weight at 10.81. All we have to do is go solve this algebraic expression, which just requires a little bit of finesse, just requires a little bit of factoring here, a little bit of rearranging. You know, I don't know how much time we want to spend here, but I'd have 10.0 times the fraction of 10 boron plus 11.0 AMU minus 11.0 times the fraction of 10 boron equal to 10.81. You guys see how I just did the factoring, then I'm just doing some rearranging of the numbers, and then I might want to combine these numbers here. Might want to subtract 11 AMU from both sides. So I'd have negative 1.0 times the fraction of 10 boron is equal to negative 0.19 AMU. So the fraction of 10 boron, the fraction of that lighter isotope, would be equal to 0.19. Just from negative 0.19 divided by negative 1.0. So probably the silliest algebra problem that comes up is a problem like this, but it just is like from a summation. It's just knowing what the summation means, knowing that we can sum them up, and then try to solve a math problem that gets us towards what it is that we're looking for. If it's the fraction of the lighter isotope, 0.19%. What's the fraction of the heavier isotope? Well, of course, it's just 0.81. 19% one, 81% the other. So just making sure we see how to do the math on a problem like this one here. Let's think about some cubic conversions, or conversion factors in general out of chapter 1. So what's the volume of a pole in liters where we have the length times the width times the height in meters? So what conversion factors do I want to know as it relates to like a cubic length unit in liters? Is probably just one conversion factor I really want to make sure we all know. That would be that 1 milliliter is exactly 1 cubic centimeter. That's all we need to know to do this conversion. So this is the big thing that we just need to know. And then the other conversions that we kind of need to know are centimeters to meters. That's easy, right? 100 centimeters in a meter. And then 1,000 milliliters in a liter. So just using those metric prefix conversion factors. And so the way I might think about doing this problem here is, since I want to convert cubic centimeters to milliliters, why don't I just convert all those meters to centimeters to start with? So why don't I start this as 500 centimeters times 850 centimeters times 250 centimeters. So I can calculate the volume in cubic centimeters and not even have to do one of those cubic conversions. So 500 times 850 times 250, having converted meters to centimeters, gives me a big number. I'm going to switch to scientific mode so I don't screw it up, but it's 1.0625 times 10 to the 8 cubic centimeters. Now let's do one other thing real quick. Let's just do the 5 times 8.5 times 2.5 real quick in meters. Let's say we didn't convert it. If we didn't convert it, that would have been 106.25. So let's say we did the problem a different way and we didn't convert to cubic centimeters. We just left it in cubic meters. We would have gotten 106. Let's just make sure that we see this conversion here again, this idea that if we want to convert this to centimeters cubed, that this isn't the conversion factor. This would be the conversion factor. So we need to use 1 meter to 100 centimeters where we cube the entire conversion. So cube the 100, cube the centimeters, cube the meters. And so then this times 100 cubed, which would be 100 caret 3, is 1.06 times 10 to the 8. So being able to like handle or just like do that type of cubic conversion just comes up, and that's going to be something you'll see on the test. You know, just like making sure we understand how to deal with problems where we're converting a cubic length unit like meters cubed to centimeters cubed. And sometimes there's ways of simplifying it. Like I simplified it here by just going to centimeters and not even having to do the actual cubic conversion in the problem. There's always ways to simplify problems. But once we get the volume, all we need to do is recognize that, of course, that's just a milliliter, 1,000 milliliters in a liter. So divide by 1,000, 1.06 times 10 to the 5 liters, because the question was asking for liters. So a lot of times with conversions, it's just the savvy to know either how do I cut a corner, or just how do I know what units things are best in. You know, like when I'm looking at this problem here, we didn't tell you that you needed to convert to centimeters. We didn't tell you, if you didn't, that you needed to convert to cubic centimeters. Those are things I think are just kind of like part of the process of just knowing how to get the liters is to get to cubic centimeters because of the link to milliliters, and then the link for meters to centimeters. So not like you need to memorize conversion factors here, just a matter of using some key ones. Sig figs, hopefully this page here is good review, except for the last question is kind of a tricky one. But 50 plus 74, let's not out-trick ourselves. When we're just assuming all of these are inexact quantities, this is just one sig fig. So 50 is just one sig fig, not two. Even though it looks like it's, like, why would 74 be good to the ones but 50 not? It's really weird on how we're going to see 50. We'd have to be told something about that 0 to know it's significant. Otherwise, just one sig fig here. So I see 50 plus 74. I'm rounding this to 120. Okay. And so sometimes it's easy to out-trick ourselves on a problem. You know, the real weird thing would be thinking, well, if 74 was good to hear, why wouldn't 50? Well, if it was, we would have written it as maybe this, or maybe we would have written it as 5.0 times 10 to the 1. If we want that 0 to be told to you is significant, we would give it to you a different way than just writing 50. What about the next problem? 3 sig figs times 3, so that should have 3 sig figs. Let's do that math real quick. 16 times 1.25. That's, let me get out of scientific mode. So that's 20, but 20.0, because it needs to have 3 sig figs. Do this math here. 1.25 plus 3.75. That's not just 5, that's 5.00. Let's take a step back. If you put this in your calculator and you see 20, it's easy to outsmart yourself and think, oh, he just said that's just one sig fig, right? Did anybody think that? Maybe you would have thought that a week or two ago. Hopefully we've moved past this, but if you had thought my calculator said 20, isn't that one sig fig? It's not one sig fig because we knew it was 3 times 3. From the nature of the information in the problem, we know it has 3 sig figs. So the way the information is told to us is how we interpret we have 3 sig figs. Same thing with here. Even though my calculator just said 5, I'm smarter than my calculator, hopefully. And so I know that's 5.00. And this works out to 4.00 to 3 total sig figs. So 3 sig figs here. Now what about this problem here? If we just put this in our calculator real quick. The exponents kind of trick us here, but we might look at this and think that it should be 1.26 times 10 to the 5. But that would be wrong. Because you may be thinking, well, how do I not get 3 sig figs in my answer here? And it all has to do with the way the exponents are working. Like, what if I just had 4.74 plus 7.87 without the exponents? Like, just as those numbers. If this was the problem, wouldn't the answer be 11, or whatever it be, 12.61? So the answer would have been 12.61 to 4 sig figs if we got rid of the exponents and didn't have the times 10 to the 4. So how does times 10 to the 4 change this problem? Well, it doesn't really change it. It just means we might want to think about writing the numbers out or being a bit more clear with the arithmetic. If I can be more clear in writing, that would be great too. And so what I might think here is just express the numbers as their true numbers as a whole number instead of the exponent value. And then let's do these summations. So I get 12, 6, 1, 0, 0. And here I think you can see why all 4 digits should be significant. And so the answer is really, one way of thinking of it, 12.61 times 10 to the 4, all 4 digits being significant. That's kind of seeing how the math works. And also if you go to the whole number version and then go back to scientific notation, you can write this as 1.261 times 10 to the 5. So 4 digits are significant in that quantity. The exponent can be to the 5th or the 4th, doesn't matter, but hopefully either way it lets you see why all 4 digits are significant. So sig fig problems, hopefully, like, exponents are maybe the last layer that sometimes are tricky with sig figs. We see a lot of multi-step problems. They're not hard, just apply the rules and just be very clear with the arithmetic. If something confuses you with an exponent, write it out fully. If you need to use scientific notation, or if we give you a number with scientific notation, it's just to be clear with the scientific notation and the number of sig figs. All right, let's look at a formula problem from question 1. So we're told a compound has a molecular weight 4 times its empirical formula mass, and it's 88.8% carbon, 11.2% hydrogen by mass, what's the molecular formula? Well, from this information here, the percent mass, I should be able to get my empirical formula. The empirical formula is the simplest ratio of the moles of the elements in the compound. These are the mass ratios. So from 88.8 grams of carbon present for every 11.2 grams of hydrogen, I should be able to get the number of moles that would be in that sample or in those masses, and then I can try to get a whole number from there. So I'm going to use the molar mass of carbon, 12.01 grams per mole of carbon. So just go to the periodic table for carbon. Then for H, we go to the periodic table for H. So 1.008 grams per mole of hydrogen. So it gets me 7.39 moles of carbon. Now that's in ratio. Think about having a ratio to hydrogen, which is 11.1. So we got to keep that ratio intact. We just would like that to be a whole number ratio. So it's not going to round. See how it doesn't round to like C7, H11? Like there's the whole. We got to be whole numbers here. So let's divide both of these by the smallest number to try to get towards whole numbers. That gets me 1.5 moles of hydrogen present. Now I divided carbon by itself, so that's 1 mole. So for every mole of carbon, I have 1.5 moles of hydrogen. Closer to whole numbers, but still not a whole number. When I get to this point here, I start thinking now multiples. I need to multiply by a whole number. If I multiply by anything other than a whole number, carbon's not going to be a whole number anymore. So I got to go by whole numbers. So if 1 doesn't work, obviously it doesn't. In this case, I try 2. 2 doesn't work, I try 3. 3 doesn't work, I try 4. So just go up and start doubling, tripling, quadrupling. But I just need to double. So I go to C2, H3. The key is you got to keep the ratio intact. We start with the ratio of the mass using their individual molar masses for the elements. We go to moles. We divide both by the same number to keep the ratio intact. I can't divide one by one number, another by a different, then the ratio would be broken. So I got to keep the ratio intact, so I divide both of them by the smallest. And then I look for the same multiple that makes them both whole numbers. 2 works just fine. So C2H3 is my empirical formula. The molecular formula, we are told, contains 4 multiples of the empirical formula. So I just need to quadruple each of these. So that'd be C8H12. So you can't get a molecular formula without additional information. For molecular compounds, it's usually what you want. So usually you see this as like a 2-part question if it's a molecular compound. If it's an ionic compound, then usually we just want the empirical formula. So the empirical formula is fine if it's an ionic compound. What a question like 2. So what if we're told the formula is XCl3, where we know there's 3 chlorines for every 1 X. X is an unknown element. How do we solve this type of problem? I don't know if you've come across one of these before, but this problem here is really just coming down to percent mass. So if we remember the percent by mass of a given element of this compound, let's say the chlorine's mass, the percent by mass of any atom in a molecule is just the number of that atom in the formula times the atomic weight of that element. So there's 3 chlorines in this compound. Chlorine's atomic weight in the periodic table is 35.453. Divide by the formula weight of the entire unit of XCl3. So the percent chlorine in XCl3 is the 3 chlorine masses. Divide by whatever the formula weight of the compound is, times 100%. And we're told that this is 79.8%. So by them giving us the percent by mass chlorine, I can kind of think about what that means and kind of write out the formula for that and see that there's just one unknown here. that I can solve for. So let me get rid of the percent here. So let's go to a fraction just to get rid of the 100%. And so then the formula weight of the compound is 3 times 35.453 divided by 0.798. So that tells me that the formula weight of the compound is 133.3. Now from that information, can we determine X? And hopefully we can, because the whole mass of the compound is 133.3. 3 times 35.45 are the chlorines, so the difference has to be X. So the mass of X would just be 133.3 minus 3 times 35.453. So subtract the mass of the 3 chlorines from the total mass of the compound. And that's 26.9. So then we just go searching the periodic table for an element that has that mass, and that would be aluminum. Now it also makes sense because aluminum forms a 3 plus, chlorine a minus, so it even makes sense that the formula would be AlCl3. So this problem here may look tricky, but it's just using the concept of percent by mass. So it's just using the percent by mass, where it gives us that, and the formula, some information about the formula that lets us determine the formula weight of the compound, and then from there we can determine the identity of the unknown element. We see a nomenclature question here. So they're giving us here an ion we haven't named as part of our nomenclature, so aluminum oxalate, but they're giving us the information by showing us its formula. So aluminum oxalate is Al2C2O43. So oxalate must be the C2O4 ion, but the thing is we have to deduce the charge of the ion. So what's the charge of the ion? Well, let's look at the ratio of aluminum. We know aluminum's a 3 plus. That's the only charge aluminum forms with. So that gives us a total of a 6 plus coming from the 2 Als. And so then I have to counterbalance that with the 6 minus from the oxalate ions. There's 3 oxalate ions in the formula, so that means oxalate has to have a charge of minus 2. So we can deduce from the information in the problem that oxalate ion must be C2O4 with a 2 minus charge. And so then if iron were to pair up with oxalate in the form of iron 2, well, what's iron 2? That just means Fe2 plus. Well, Fe2 plus just pairs up 1 to 1. So this problem here is testing just the concepts of nomenclature. This is testing if we can determine the charge of oxalate from aluminum oxalate, because we should know the charge of aluminum is only 3 plus. That gets us the 2 minus for oxalate. And then it's also testing to make sure that we know that iron 2 plus means Fe2 plus. It doesn't mean that there's 2 irons necessarily in the formula. Sometimes we get confused on what the 2 means. The 2 just means the charge on iron's a 2 plus. And then the charges pair up just 1 to 1. So FeC2O4. What about protons, electrons, neutrons, counting up these subatomic particles and thinking of symbols? So 127 iodine minus. So the number as the superscript is always the mass number. Sometimes we write it here. So if you see it here, this is also a mass number. The mass number is where the majority of the mass of the atom's coming from. That's the sum of the number of protons and the neutrons that reside in the nucleus. The atomic number is the subscript, which is often neglected because you don't have to write it, because you can look at a periodic table and determine it. For iodine, that's 53. What what makes each element unique is the number of protons in the nucleus for that atom. So the positive charge in the nucleus drastically changes the property of the element. So 53 is the proton count. And then the difference here are the neutrons. We have 74 neutrons. And then the idea of negative charge is that we'd have neutral charge if we had an equal number of protons and electrons. So 53 protons with 53 electrons would be neutral. If we add 1 electron, we have more negative particles. That's a -1 charge. So think of the positive charge, think of the negative charge, think about the balance between the two. And so if we're adding up 53 positive charges with negative 54 particles, we get a -1 charge overall. So -1 means we have 54 electrons. Remember, we're not changing proton count easily. You're not getting into the nucleus and changing the subatomic particles by simple chemical means, but the electrons outside the nucleus, you can kick electrons on and off atoms. The non-metallic elements will absorb electrons more easily. The metallic elements on the left side will lose electrons more easily. So metals go positive in their charge states. Non-metals tend to go negative more often when they form ions. Another sig-fig example. This one here, like I remember when this question was asked on a midterm, the confusing part here is the same one as before, 20 plus 1163. Like what tool were you using that in one case allowed you to go to the nearest centimeter, and then somehow another tool, you were only good to the nearest 10 centimeter, and for whatever reason the small value had 1 sig-fig. It's such a dumb problem, but 20 here, it should just be interpreted to have 1 sig-fig. So 20, 1163, just rounding accordingly to 1180 with 3 sig-figs. You could round up, you could keep the 3 along for the next step, whatever. I think it's probably fair to round it on the test question just to make sure you don't make the mistake and miscount the sig-figs. But we'd have 3 sig-figs and then times the result of the next step. And so if I have 15.160 and I'm subtracting 0.00863, I need to keep that to the placeholder that's higher. And so that's going to have 5 sig-figs, it looks like. So it'd be 15.151. So I have 3 sig-figs times 5. I'm going to keep 3 when I do the multiplication step last. So just sequentially apply the rules as you're doing the steps and the order of operations you have to do them in. We do the addition, 1180, subtraction, 3 sig-figs, or excuse me, we end up with 5 overall sig-figs. And here we have 3, multiply them together, round it to 3. Let's talk about those experiments in early part of chapter 2. The discovery of the electron was the first major experiment that we talked about. That was the cathode ray tube experiment. That's J.J. Thomson. The order of the discovery of the subatomic particles is something I think I've highlighted more in past semesters. I don't know if that's something the test committee tends to think is that big of a deal to test, but the electron came first, just to make sure we're probably obvious, because we talked about the discovery of the electron first. So the electron was discovered first, and then the proton discovered second. You know, that's like the particle with the charge is going to be more easily observed than the particle that's neutral. The neutron was observed last. I specifically remember mentioning the year, just because I think it's interesting. The electron's like 1900, or like 1897 was the electron. I don't think I ever mentioned the proton year, but it's about 10 years later. It's around 1910-ish. But the neutron's not discovered as a particle until like 1932. I just found that wild, just like how recent that was in time that the neutron was being discovered. Curie discovered the radioactive pathways, so the alpha radiation, the beta decay, and the gamma decay. Which gamma, I always have a hard time writing the gamma. So maybe I'll just spell it out. So the alpha decay is our, well, let's start with the beta. The beta decay was the electron, or a high energy electron coming off a nucleus. The alpha particle was the helium nucleus. The gamma radiation is just high energy radiation. And so Curie was just discovering the radioactive pathways of matter. Not mentioned here was Millikan was the oil drop experiment. Millikan was the discoverer of the mass and the charge of the electron. The electron charge, the electron mass discovered in that Millikan oil drop experiment. Curie discovering the radioactive pathways, and then Millikan's and Rutherford's, I guess Millikan's was, I'm not going to describe it here, and then Rutherford's experiment was the nuclear model. The atom came about from shooting the alpha particles from Curie's experiment at a thin sheet of gold foil and seeing backscattering. So Rutherford's experiment saw the backscattering of the alpha particles. That's alpha particle. That's why I'm screwing up gamma, because I'm writing alpha like gamma. So the alpha particle, the Greek people in the room are like, he's butchering our language. So alpha, and then gamma is that way, right? Okay. So the alpha particle from Curie's work, the helium nucleus, was backscattered by collision with gold nuclei. So it allowed the discovery and the proposal of that nuclear model. So if we didn't have a collection of all those subatomic particles, of all the protons and neutrons into a single nuclei for a gold atom, when that alpha particle struck the nucleus, it never would have been deflected backwards. So you have a particle much more massive traveling very fast. If it's hitting a single neutron or a single proton, it's just going to keep going. But if it hits a collection of those particles, it can deflect backwards. So it allowed the discovery and the proposal and the validation of that nuclear model for our atoms. So that's Rutherford's work. And then lastly, a question using Avogadro's number, which hasn't come up yet in examples today. So let's use a problem that gets into Avogadro's number. How many oxygen atoms are present in a certain quantity sample of something like CO2? So a number of oxygen atoms. We're going to be thinking here grams to mole to molecule to atom. So we're thinking grams of CO2 to moles of CO2 to molecules of CO2 to atoms of oxygen on that molecule. To do grams to moles, we need a molar mass. To do moles to molecule, we need Avogadro's number. And then for molecule to atoms, we need to inspect the formula of the compound. So our number of oxygen atoms, 6.5 grams of carbon dioxide. Need to use the grams per mole for CO2. 12.01 plus 16 times 2, that's 44.01 grams per mole of CO2. 1 mole of whatever the thing is, CO2, so 1 mole of CO2 contains an Avogadro's number, 6.022 times 10 to the 23 of whatever CO2 is. CO2 is a molecular compound, so we get a Avogadro's number of CO2 molecules. Now you don't have to know the bonding nature between C and O, but other than that there's 2 O's connected to a single C, that's 1 molecule of CO2. It's specifically 2 O atoms connected to 1 C atom. And so 1 molecule of CO2 contains 2 O atoms. So we're just doing 6.5 divided by 44.01 times Avogadro's number times 2. Gives me 1.78 times 10 to the 23. So we can go the other way. Like you could say, in fact, we have another minute or two. What if we said in like part B or second example, you had a sample of CO2 that had, 4.83 times 10 to the 24 O atoms. You could then say how many CO2 molecules are present, or how many grams of CO2 are present. So for us to be able to have within a CO2 sample 4.83 times 10 to the 4 O atoms, how many grams of CO2 would be present? This is just going the other way, going back to grams, starting from O atoms. There's 2 O atoms per molecule of CO2. There's an Avogadro's number of CO2. Per mole of CO2, and then 1 mole of CO2, 44.01 grams. So we can run the math the opposite direction. So if I had this count of oxygen atoms, then we'd have 176 grams of CO2 present. Just showing you can go from grams to atoms, or you can take the atom count and go back to grams. It's the same math no matter which way you're going. Conversions are the same, just a matter of what steps we're doing them in and what's in the numerator versus what's in the denominator. So just follow what's in the numerator with what's in the denominator so it cancels. So molecule cancels, mole cancels, we get grams that we're looking for. All right, that kind of wraps up our class for today. Good luck on the test tomorrow. Office hours today till 1 and then 2 to 3, 2047 McPherson. Head on over if you have questions. Bunch of practice is available. Good luck to you guys.